Okay, we should begin. Okay, and we're good to go. Yeah.
All right. Today I would like to talk about iterative acceleration techniques. In this audience, Green's functions don't need any introduction, but still, let me just remind you what we're interested in. We're interested in Matsubara formalism, formulated in imaginary time. We work with imaginary time Green's functions, defined as a time-moderate product of annihilation and creation operators in the Heisenberg picture. And so we work with self-consistent methods, solving the DIIS equation self-consistently. Here, G is a full Green's function, G0 is a Green's function of independent electrons, and sigma is a self-energy. And of course, we use approximations for self-energy, and the approximations define the self-energy function that depends on the full Green's function. We may work with the Hartree-Fock approximation, the lowest order approximation, or we may work with correlated theories, such as GF2 that includes second order direct and exchange terms, and GW that includes an infinite number of terms like this. So the calculation is usually set up in this manner, that we start with the initial yes for the Fock matrix or for the self-energy, and then we use the Dyson equation to find G at a given Fock matrix or self-energy, and then we may evaluate the Fock matrix and self-energy given the functional form. And then we may extrapolate the set of obtained Fock matrices, self-energies, or maybe damp them. And then we can solve the Dyson equation again. If we want to preserve the number of electrons that we want, we may optimize chemical potential. Then we may evaluate energy, and we repeat the cycle. So this is the way how it is implemented now in the UGF2 program. And the purpose of my talk is to talk about the possibilities for extrapolation.
Pavel,
yes.
Turn the camera just a little bit that you can see it.
This one. Okay. Okay.
Yeah, I think now you can see it. Thanks.
Okay. So most of the time, simple damping is used, that is defined here. The Fock matrix, the resulting Fock matrix is obtained as a mixture of the Fock matrix from the previous iteration with a constant weight alpha, and the same is done for self-energy. Damping usually leads to convergence and usually stabilizes iterations, but the problem with it is that it is very slow, and many iterations can be required to reach the convergence. Previously, there was some progress in the accelerated methods. Chianon implemented his version of DIIS that uses difference residuals. However, some results from that code were hard to analyze because sometimes it behaved more slowly than damping, and it wasn't clear why. So I decided to separate the implementation of the algorithm from the problem. So to localize the issue, to figure out whether it is a problem with the code or with the algorithm. So I implemented DIIS and several other algorithms in a completely general way that does not know anything about Green's functions. So it is just a general code that operates with vector algebra. And the advantage of that is that I can test it, for example, on linear systems of equations or on some other problems, just to make sure that the algorithm is correct. So I implemented DIIS, I implemented Chem or cryospace accelerated inexact Newton method, and LCIS or least squared commutator in the iterative subspace. I also implemented several types of residuals. The difference residual, where the differences between self-energies is taken as a residual, and the generalized commutator residual. If we take the Dyson equation and multiply by G from the left and from the right and take the difference, we can arrive to this commutator, which is a direct generalization of the commutator residuals commonly used in Hartree-Fock calculations, where the commutator between the density and the Fock matrix is used. Let me just go through the conventional DIIS definition, and then I will tell what the features are in the Green's function methods. So in DIIS, we have a sequence of vectors Vi that converge to some target vector V star, which we interpret as a solution. We can always write the vectors Vi as a final vector V star plus the error Ei. Now, in DIIS, we seek a linear extrapolation of the vectors Vi, and we can write it down given this representation. And if we want to have a sequence of extrapolated vectors that reach the convergence, we can immediately see that we must have a necessary constraint on these coefficients, that they must add up to 1. And the remaining part is called an extrapolated error. And the DIIS is formulated as an optimization problem that minimizes the squared norm of this extrapolated error. How it is done mathematically, we use Lagrange multipliers, where we write down this squared norm as a quadratic form, depending on overlaps, and this constraint is built into the Lagrange multiplier into the Lagrangian. And then we can take the derivative of this Lagrangian, equate it to 0, and obtain this set of equations. Now, we may have, in general, we may have complex extrapolation coefficients because the self-energies are complex that we put as vectors. But if we think a little bit about it, we have a set of inequalities associated with causality, and once we have coefficients that are not non-negative, we may violate some of these inequalities. So maybe it's better to constrain the coefficients such that they're real or maybe even positive. So far, if we say that they're real, then only real part of this overlaps appear in the system of equations, and it seems to be very stable. And the magnitude of these coefficients can serve as some sort of diagnostic of how well the DIIS extrapolation is performed. So if the coefficients are very big, then the extrapolation is maybe not very good. Now, in LCIS, in the original formulation of LCAS done for Hartree-Fock and DFT, both the Fock matrix and the density are extrapolated with the same coefficients, and then the commutator between the extrapolated quantities is assembled, and under DIIS constraint, its norm is served as an objective function. So here we can do something very similar. We can extrapolate self-energy, and I mean both Fock matrix and the dynamical self-energy, and the Green's function with the same coefficients. We can compile a commutator from the extrapolated quantities, and we can put the necessary DIIS constraint on coefficients, and we can say that okay, this is the norm, the squared norm of this commutator is our objective function that we want to minimize under this constraint. And for this purpose, again, we can compile a Lagrangian, but here, because this objective function is a quartic function, so here, since it is not a quadratic form, it won't lead to a linear system of equations, and we need some iterative procedure to solve it. So in the original publication, a Newton method was used, but it didn't have some sufficient details of how it is implemented. So, so maybe there is some freedom of how it can be implemented. So I implemented a Newton method for solving this problem with backtracking line search. And because it is a constraint optimization, put some safeguards with a tangent gradient projection to make sure that the step does not step out of this necessary constraint. So Kane formulated it somewhat differently. So it is formulated not in terms of objective functions, but in terms of approximate Newton method. So the goal in Kane is to find the root of the vector equation, and the new vector is interpreted as a current position of a vector plus a step, and the step is found from the Newton, from just Newton method. Of course, in practice, when we don't know the exact Hessian, we may want to approximate it, and in the subspace methods, there are ways to do that. So here, the Jacobian is approximated just considering finite differences between the subspace vectors, and this directly leads to the action of this Jacobian on the vectors that we can plug in. Ideally, we may want to use some type of preconditioning to define the action of Jacobian on vectors, but here preconditioning is unknown. So when we go to a subspace formulation, we can split the sequence of vectors into the space of the differences and the outside space. The action in this subspace can be obtained through this finite differences, but the action from the outside space is not really known. So we can either precondition it if we know the problem value, or if we don't know the problem value, we can just say that okay, maybe it's close to 1, and in practice it doesn't matter that much for the problems that I looked at, because this component is very small, so the exact preconditioning is not that important. So once we plug it in, once we say that okay, this projector acting on the space of the differences is some linear combination of the space, and once we plug it in, we arrive to a set of linear equations for coefficients. Here, the matrix A is compiled from the differences between the vectors that we want to solve and the space of the residuals that we want to minimize to 0. The structure of the system actually tells us something that will be apparent later, but it will be kind of hard to deal with. So we have less degrees of freedom than in DIIS. So in DIIS, we can choose whatever residuals we want, but here we must maintain some caution. For example, commutator residuals don't work with Chem because it will lead to the ill-defined system of equations. So let's see how it all works in practice. So this is a very simple example, probably the simplest that I can come up with. So this is just a beryllium atom. The iterations start from the 0 temperature Hartree-Fock gas, and these are the GW iterations. So here on the vertical axis, I show the changes in the density matrix that are printed in the output as DMD. And on the horizontal axis, I show the iteration number. So the temperature is pretty high, but not that high. So the character of the final solution is very similar to a 0 temperature solution. And the dimension of the subspace is kept just by 2 vectors. This is the minimal subspace to make a fair comparison with damping. So what do we see? We see that when we use the difference residuals, both DIIS and Chem lead to highly oscillatory behavior, and the quality of these iterations are really very similar to damping. So we don't get any advantage when we use difference residuals for both the DIIS and Chem. When we use commutator residuals, we have the opposite picture. Both commutator DIIS and LCIS behave very well in the beginning, but then they enter some numerical noise. So if you need a really tightly converged solution, I recommend to switch here from the iterative procedures just to simple damping to converge it up to the numerical accuracy. So yeah, it is the difference in density. So it is the norm of the difference between the density matrix in the subsequent iterations, and it is printed as DMD in the output. So what happens when we increase the temperature? The difference residuals diverge. So they go bananas. And I tried different ways of constraining them such that they don't diverge that much. But I can say that whatever I do, I cannot outperform a simple method. So maybe the difference residuals, the difference residual choice is not the best option, but the commutator residuals behave very well and very stable. And I think the reason in this behavior is the following: that when we define an error as a difference residual, we're really biased toward self-energy. So when we use difference residuals for a quantity x, we may obtain a good approximation of x, like a good extrapolation of x, but it may not be a good approximation for 1 over x, right? And this is why the Green's function and the density matrix misbehave. So in order to obtain a fair extrapolation for x, we must also take into account 1 over x in one way or another. So commutator residuals take it into account, and we have kind of fair game for both self-energy and Green's function, and it seems to be pretty stable. So since many people are interested in solids here, these are some results for one of the solid that can be shared with me. And so I can run whatever algorithms I have. The iterations start from a DFT gas, PB0, and then you can see an interesting picture that if you use damping, it may lead to some illusion of convergence, right? So for example, not a very severe damping can be used here. So first it kind of converges and then it diverges. And if the damping is more severe, it kind of again converges, but then stops converging. So maybe damping is a little bit dangerous in this respect, that it may lead to some illusion of convergence when there's not actually a convergence. But it looks like the subspace methods with commutator residuals are very stable and similar to each other. And I tested it on a number of solids. This one, vanadate, nickel oxide, a few others, and it seems to be working fairly well. So there are some examples that are still challenging, and I want to just to say what they are, so you can be aware of it and maybe have some ideas how to solve it. So if we go to restricted versions of the methods, then in strongly correlated systems, it's easy to end up to something poorly behaved. So this is a very simple example. This is a stretched hydrogen molecule that I tried to run with restricted GF2, starting from a restricted Hartree-Fock gas at low temperature. And here the iterations go bananas, and it doesn't matter how severe damping I use, so it doesn't converge, and the commutator methods also don't work if I execute it in this manner. So what can we do? So it seems to be a challenging problem, challenging convergence that limits the application of the restricted methods. It turns out that we can think about the physics of what is going on. If we go to high temperature limit, then we can disable the correlation completely. At the high temperature limit, the Hartree-Fock method becomes exact because all the correlation is disabled. And if we heat the system to a high enough temperature, then we can effectively disable the strongly correlated part of the problem and make it weakly correlated. And then maybe we can cool it down and converge it back. And it seems to be working pretty well for a number of cases. So I tested the hydrogen molecule, all sorts of clusters with hydrogen cubes, and breaking of multiple bonds or high bond order. So this is a stretched nitrogen molecule where the triple bond is broken. Pretty strongly correlated system. So if I heat it up to high temperature, then the restricted Hartree-Fock converges very quickly. And if I start from it, the restricted GF2 also converges without any problem. Now, if I take the restricted GF2 solution from it and decrease the temperature and start from it, then again, the convergence can be easily reached. And then I repeat the process. I take the final solution and reduce the temperature and run it again and again. And in this manner, one can really arrive to a very low temperature and obtain the restricted GF2 solution for a strongly correlated case. So here, once the temperature decreases, the correlation becomes stronger. And in this regime, the subspace formulations indeed become superior because the subspace vectors stabilize the iteration. So here I need at least 5 subspace vectors to make sure that all the iterations are stable. And there is no apparent winner. So here I show both DIIS and LCIS. Sometimes one is better, sometimes another is better. So they are very comparable with each other. Okay, we have a recently published paper on that. So if you would like to know some minor theoretical details, please take a look. And now I can transition to a more practical part. where I can tell you how to run all of the stuff. So so the code is available within UGF2 suite, and it works for Hartree, GW, and GF2. The implementation is very general, so if you implement some other method, it still will work with something else if you would like to have it. And it works both for solids and for molecules, so it is completely general. However, there are a few limitations of the implementation. I was more interested in the correctness of the implementation rather than in speed, so I didn't put MPI parallelization, but it doesn't seem to be very important because the cost of evaluation of self-energy is much larger than the cost of the evaluation of overlaps or commutators. Unless you want to run enormous number of iterations, this does not this is not that important. At least I run pretty big systems like nickel oxide with 6x6x6 grid, and I didn't really notice like this step. So the just a single GW iteration is much more expensive than all the overlaps. So also, it's not very clear how to implement the restart, like whether one wants to recover the whole subspace or maybe some part of it. So at the moment, I have only kind of limited restart, right? So basically, all the old functionality works, but I don't rebuild the entire space. So if you want to restart the calculation, first it will build the extrapolation space and then continue working with it. But I will talk about like how to restart the calculation correctly. And also I have a very experimental feature which I call micro iterations, but it may be known for by some other names, where only where the self energy is freezed and the updates go only to the fork matrix, and then the self energy is unfreezed. So from my understanding, this feature was around in the old code, but it is not yet in the new code. And I can give some comments about that too. So how to use it? I implemented it in the way such that I reused the most number of keywords from the previous implementation, and both implementations are available. So DIIS code uses 3 parameters. The Chen's implementation of DIIS uses 3 parameters: DIIS size, DIIS start, and DIIS interval. So DIIS size defines the subspace size. DIIS start defines when to switch from damping to DIIS, and the DIIS interval defines which iteration perform DIIS extrapolation. So my code doesn't use the DIIS interval, so it just uses the extrapolation at all the iterations, and this does not seem to be a problem with the commutator formulations at all, but it is a problem with the difference residuals that I don't recommend to use. So in order to activate my code, a user must specify a new DIIS equals true, and if one wants to use the commutator version, com_DIIS equals true should be used. It will activate the commutator residuals use. I played with trust region techniques. So basically, if the extrapolation coefficients are very big, then the extrapolation may be very poor, as in the case of the difference residuals. So I put some constraint, like how big the sum of the absolute values of the coefficients can be. But may not be kind of optimal, right? So, but basically, this parameter specifies it as a default. I set it to some big number, so it probably doesn't matter in practical calculations. so far, if you use a commutator formulation, then the coefficients are fairly small, and this is not needed at all. And here are the recommended settings. I don't recommend to go to a very big DIIS size. Usually, if you have a weakly correlated system, small subspace size works very well. Something about 3 to 4 vectors. And if you go to a very big subspace sizes, in this case, it can slow down a little bit because it will use it will damp it a little bit too much. But if you have a strongly correlated system, then maybe going to a bigger subspace sizes is necessary because it will stabilize the behavior of iterations. But again, it shouldn't be too much. So for nitrogen molecule, just 5 subspace vectors was enough to have a very stable convergence. And DIIS start when the iterations should start. In practice, I see that if you so it depends where you start. So if you start from a DFT guess and let's say run GW, then the changes are pretty big. So maybe DFT is not a very good starting guess for GW. So I find that it is much easier to converge GW if you start from a hard-fork guess. Then the changes in the fork matrix are not very big, and the conversions can be reached in fewer iterations. I usually put it 2 or 3, and it seems to be working fine. So when DIIS start is less than DIIS size, my code just uses the available subspace. So if it does not have enough, so if it has a number of subspace vectors less than the specified DIIS size, it will just use the available subspace vectors for extrapolation and then grow the subspace size until this limit is reached, and then drop the old vectors. So this is an example of an output for nickel oxide that I used recently. So everything is just as you usually use the calculations, except this part. So here I put these new parameters. Well, you can drop this one, so it's not that important. But yeah, just this is how it can be used. Yes.
You have a damping parameter in there of 0.2.
Yeah. So not in the beginning, right? So at the first iteration, like before this DIIS start, it will use damping, and then once iteration is reached number 5, then it will switch to DIIS. So it is needed for the first iteration just to make sure that they don't go bananas.
And the damping of 0.3 means that you get 0.3 of the new solution and 0.7 of the old.
Yes, that's correct. So you can also use LCIS. So you don't need to specify new DIIS or home DIIS parameters to do that. So you can just say LCIS equals true. And so I also looked like how one can avoid this numerical noise near the convergence. So I put this parameter LCIS threshold here. So it's a switch to this direct damping like iterations where the commutator evaluation is not used and the subspace is not used, just straight iterations in the end, just to avoid this numerical noise. It seems to be fine for molecules, but in solids, honestly, I can never reach this regime where this noise appears. So in solids, I can go straight like 10 to the minus 7 in density matrix and energy, and the noise doesn't show up. So at least in nickel oxide and then in silicon. So maybe for solids it's not that important. And I use some variables from DIIS, such as DIIS size, just to specify the subspace size for LCIS, and DIIS start to specify when the iterations should start. So one of the caveats of LCIS comes from the fact that it uses the commutator between the extrapolated Green's function and self-energy, and effectively it is a quartic function, right? And that's why it uses in total the number of commutators as the dimension of the Fock space to the sorry, the dimension of the subspace to the fourth. So it can scale quite badly with the size of the subspace size. So I recommend to keep it reasonably small, like 2 to 4, maybe 5 if you have a nitrogen molecule, right? But don't just like DIIS is more forgiving, right? With in terms of cost with the subspace size, but LCIS is worse in terms of scaling. So keep it small. And finally, if you want to use Chem, you need to be aware that it can work only with the difference residuals, because the commutator residuals lead to an ill-defined set of equations, so it won't work at all. So you need just to specify Chem equals true if you would like to use it. However, in practice, I see that it behaves very similarly to the DIIS with difference residuals. So I cannot really find the case where this external correction is very big. Theoretically, it is known that when this external space correction is negligible, then it is almost exactly as DIIS. So one of the aspects is how to restart the calculations, since the calculations are very expensive and can take some time. I can tell you what I usually do. I didn't test it very well in other regime, although it seems to be working. My implementation stores the subspace on the disk such that it is not stored in memory. And so I store the vectors in DIIS, or I store on disk, or I store the residuals on disk. So in order to restart the calculation, I recommend just to remove these files, but don't remove your simulation file. And then you can specify restart equals true. Maybe you can put the DIIS start at some early stage. Then you can restart the calculation. So if you are unsure which damping you want to use, you can look at the previous iterations and just steal damping as one of the extrapolation coefficients. It seems to be working. At least it can give you an idea what damping parameter should be. I also tried not to remove this, and it seems to be working, but all what I'm saying is that it is not very well tested. So, and finally, this is a highly experimental feature with micro iteration. And so what it does, first it does full update, does extrapolation, and then it runs a bunch of cheap iteration where the dynamical part of self-energy is frozen, and the updates come only to the Fock matrix. And I implemented only commutator DIIS for the subbase of the Fock matrix, but the macro iterations can use whatever else is available. It is a somewhat experimental feature, and although it seems to be correct, in practice I see that sometimes it works. So for very weakly correlated systems, it leads to fewer expensive iterations. However, when I look at something intermediately correlated or strongly correlated, what I often see is that the iterations kind of stuck. And I think the reason behind it is that if the self-energy is strong, then the gradient may point to the opposite direction of the Fock matrix, and they kind of pull each other to the opposite directions, and the result is kind of stuck in between, and the convergence is not reached. But still, if you would like to play with it, if you would like to look at it, there are two parameters how you can activate it. So you can say like how many micro iterations you want. Like you don't want like 100 micro iterations, maybe a few, just to run a quick update of the fork matrix. So for example, micro itermax equals 10. And you can also specify the commutator DIIS subspace for the micro iteration as shown here. Micro DIIS size equals to something. And that's it. I can answer any questions.
All right, thanks. So I have lots of questions, but maybe somebody else first. I guess the biggest question that I have is one that I'm not going to answer. If you have multiple couple self-consistency groups, right? So here micro iterations do some of this. You have an adjustment of the fork matrix, but you keep the dynamical part of the self-energy constant. But you could also think of self-energy embedding, where you have a sub part of the self-energy that changes when you keep the dynamical part of the rest constant, and the sub part of the fork matrix that changes by the rest constant. So convergence acceleration. Like, how do you deal with that? Have you thought about this? Is there a clever way of arranging those different self-consistency loops, like doing one as inner and the other one as outer?
Oh, the honest answer is I don't know. So I thought about it a little bit, but not that in detail. In the simple setup, I can already say that it doesn't always work, right? So sometimes it just goes bananas, and when it goes bananas, it is actually easier to just use full iterations all the time, and the commutator residuals seems to correct it pretty well. So this is so this weekend I ran an example with nickel oxide with a I think it was a high spin solution. I can and from it was a GW calculation starting from UHF. So if I run micro iterations, at first they kind of speed up. So the changes in the density matrix are like between macro iterations are smaller than in the full in the full iteration case, but then like when they become like 10 to the minus 4, there is kind of stagnate, and the full iterations are much better. So I don't know if this is the case with the self-energy embedding theory or not. I honestly don't. But
I think it would be very interesting to go and look more carefully at this. First of all, it's practically interesting to a lot of us, but I think it's also theoretically interesting.
But you need to have a different. So Pavel, there are completely two decoupled self-consistency loops. So each one would require most likely its own DIIS, unless we could intermingle the steps.
Yeah, nobody tells you that you have to have one as an inner loop and the other one as an outer loop, right? In fact, you could even replace inner and outer loops.
Yeah, but
what is best? Is there a mathematical argument that says one should do it, one way or the other way? I don't think it's clear at all.
I think it would be different for different examples. So it's like in many of the SEM CSTMs, right? You can redefine the order of the loops, and that usually depends how much orbitals that you adjust. So here it's kind of the same.
so here I have just only a guess based on some intuition. I cannot kind of prove that it is exact, right? But I think when the self-energy becomes big, then the changes in the fork matrix and in the self-energy kind of point to the opposite direction. So if I optimize the fork matrix, it drags in one drags the iterations in one region, and the self-energy kind of drags in another region. And altogether needs to be considered. Like for restricted calculations with broken molecules, this is pretty important. So I cannot use micro iterations just to converge you in a hydrogen molecule. So only full iterations needs to be used.
All right. The next question I have is about Anderson equation, which is a concept in numerical analysis or convergence acceleration. And so last time I talked to a numerical mathematician about this type of stuff, he said that, oh, yeah, the DIIS just looks like Anderson equations. Are you aware of that literature? And is that correct?
A little bit, but so I read a little bit about that, but the problem is people mean quite different things, like what the Anderson extrapolation is. So and even what the damping is, right? So one may have the simple dampiness here, or one may define a dynamical damping where this damping parameter is optimized in one manner or another manner. So conceptually they're very close, right? But in the actual aspects, how it's formulated, I can see some differences. Like I think the Anderson extrapolation is more close to the dynamical damping, right? Where the iterations are written through continuous fraction.
I guess the last question that I have is, we're just going to simulate, let's say, a standard solid. It's your first time looking at that solid. You have no idea what the solid is doing. What should you use? Which one of your various methods is like your first go-to that we should just try?
Okay, so since the code works with the guess, so one needs to obtain the guess first, and if you can obtain the Hartree for guess, it's great. So here I would say that there are two different regimes, right? So you can do either the restricted calculation or unrestricted calculation. The restricted calculation is typically much harder when you have strong correlation. It's harder to converge. So maybe it's easier to deal with the unrestricted calculation, and then if you want to go to a restricted one. So you can first get the unrestricted guess. The Hartree Fock seems to be a better guess than DFT, so maybe DFT is not a good guess. And then my recommendation would be to use the commutator formulations, either commutator DIIS or commutator LCS to converge GW population.
Okay. So basically, go-to is Hartree Fock starting density matrix and then commutator DIIS.
Fock matrix. So it starts from the Fock matrix.
And so okay. And another question, and I'll shut up. The method that you showed for cooling down, right? That's frequently used in classical physics for spin systems for simulated incline. And very often these things get stuck in like unphysical states, so that you have to sort of jiggle them and heat them up again, and then they'll fall into different But here there's no way of jiggling anything, right? Everything's sort of deterministic once you have your starting density matrix specified. So do you ever get stuck?
So I tried it for stretched hydrogen, for hydrogen cube, and for nitrogen molecule. Nothing gets stuck so far.
So there these old, well, not old, Dominica's paper for hydrogen solids, where you had first order transitions and multiple coexistence solutions.
Okay, so yes, there could be multiple unrestricted solutions, right? But so far I couldn't really get the multiple restricted solutions. So I can run hydrogen solid just to test it to see. So far I didn't see anything like that.
How you cool down?
Yeah, that's actually
The procedure of how you cool down.
Just change beta in the input. Just
take
take the Green's function, like take the converged self energy from the previous temperature point, use it as a starting. Seems to be working.
Wait a minute. Do you use information about the dynamical self energy, or do you just use the Fock matrix?
Both Fock matrix and the dynamical self energy as a
So
starting.
the dynamical self energy lives on 1 to points. And as you change your temperature, the multiplier points shift. Do you do anything to interpolate?
I know.
You just reinterpret and it's doing just fine.
But
You
the
would
problem
just
is
like it.
restarting.
So the problem is because we use this non-equidistant grid, so you have like this slope of the Green's function and self-energy on the border of the from your beta. And when you change your beta, so you expect that your like this curvature should be the same. But when you change your beta, so basically, I mean, you expect that your curvature for the high temperature should be more flat. Or not flat, it's more like more rounded. And if you cool down, it should be like more sharp. But when you just change beta and you do not read, like you do not do any interpolation of your data. So this data is basically it's some random guess basically. It's not actually like higher temperature value for that starting point.
I don't think that it is random because see, the functions are analytical, right? So it means that if I differentiate like whatever.
I mean, the functions are correct in some sense, but it's not basically the extrapolation from the high temperature to the lower temperature.
There is no extrapolation, so I just take as a simple guess, and it seems to be working pretty fine. So the change of the temperature, of course, should be fairly small, right, such that the weights are not disturbed by too much. But
So I understand what you're doing. I think what Sergey and I are trying to get at is that there might be a very easy way of doing just a little bit better.
okay,
The reason is that the self-energy, the self-energy lives, as Sergey says, lives on a non-uniform multiplier grid. Right? As you change your temperature, the points on that multiplier grid move quite a bit.
of course.
Unless you now reinterpolate or reevaluate your self-energy of the shifted points, you have just skewed your curve.
No, but this is what Pavel is doing, right?
No, he's
Because
not.
Pavel, yes, because in the restart, like when you restart, we start evaluating the self-energy again on the shifted grid.
It is so first it is read like as an array and as a guess. Then the Green's function is constructed on the new grid, and then everything is evaluated.
Yeah, the Green function is evaluated on the new grid for self-energy that was valid for the old grid.
Yeah.
And the self-energy would have to be interpolated on the new grid in order to be, just a cooled down version of the self-energy that we
Yes,
have.
but once the iterations hit like certain point, then the self-energy is also reevaluated.
Of course,
Yes,
yeah. But this is about the starting solution, how you get the best possible starting solution.
Sure.
Just trying to understand what's going on.
Yeah. But here, so
if
I
you roll your figures Pavel, for this like coming down, you see there is like a bump on the first iteration.
Exactly.
And this bump is exactly probably because of that.
could be. So sure, yeah. But it all seems to be working. So it's not.
An easy way of trying to do better, but we would have to look into that a little more carefully. With the point rate that we have, it's very easy to interpolate, right? I mean, you have to give us
It uses because you need to, if you want to. So the proper way to interpolate it is basically you have a self-energy of the multiplier frequencies, and then you need to extrapolate to the lowest multiplier because your lowest multiplier
is now just a little bit to the
it's
left.
not somewhere like in the middle, it's somewhere to the left where you don't have any data.
Yeah.
And that sometimes gives you some sort of like bias noise of 10 to the -7.
So with the Chebyshev stuff, this was, at least it was well defined what it should be. But with the IR, I don't know. Anyway, this is a discussion.
Okay, you may gain something here, like for the first couple iterations, but I'm not sure how productive it will be.
It
Like
might be 10 iterations.
No, but 10 iterations, come on, 10 iterations, like look out of 60, one has a better, I think, use out of that. The only danger is that, yes, the only danger is that this biases the convergence to some sort of, like a different stable form. But then what one can do, right, when one restarts, one can start the DIIS a little bit later. So one can do a couple of iterations, I think, without without extrapolation, right? With dumping from the previous solution and then start DIIS. So that's
Yeah, it's exactly what is done, right? So the dumping is done in the first few iterations, and then so whatever I do is working, right?
Yeah. So let's leave it at that, and if we ever have time to move on, because it doesn't.
I think that if we want to revisit it, we also would need to have more examples that point that, there is like real problem, right? Because right now we would be fighting with maybe a problem that is not really existing. So one thing that we are not, converging to this sort of local minima here. So we probably know for this N2 and the hydrogen, right, that we converge to this sort of lowest solution that should be RHF, right? Like solution, not to the, that we converge, for example, to the singlet, not to the triplet. After the cooling.
Well, I need to evaluate that square just to see what it is. I haven't evaluated it, but from the okay, I cannot say what it is from the occupancies, but it's first of all, it seems to be symmetric, so it respects the restricted structure. I can't say whether it is singlet or triplet or what it is. I really need a square.
Because I guess that it's possible that we could converge like to some of this sort of, not to the lowest solution, but to some other solution. But there's no way diagnosing to that.
But the occupancies are close to 1, so if I look just at the occupancies, they're close to 1. So.
Do we have a question over there? Any more questions from anyone? All right, so I think in that case, let's thank Pavel again. Here's one thing that I would like to do before everybody leaves. We have quite a few new faces, so I wonder if everybody could just introduce themselves and say what they're working on and where their office is so that they can be found. All right, so everybody knows Dominica, right? Cannot be found.
Cannot be found. Ask Chana or Sierra with exact guidance, but it's 2000 at.
All right, Pavel, we've just seen. Gianna, why don't you introduce?
They all in 2000 office, but currently in the process of coming back.
Hi everyone. My name is Shannon. I'm with the student members group, also with Dominica as well. My office is in 2409.
And Gianna,
Yeah.
a lot of these EW, too, that's all. So.
Yeah, I'm working on the raw material simulations.
Yesterday you learned that you sit in Durand.
Yeah.
No, you don't. You sit in all right.
Yeah, I'm doing already.
In Ordrando.
I'm using. I'm a graduate student in the university. I'm working on using machine learning to kind of DF2 functional. We can train results for these function-based methods, so we can simulate
Thomas, I'm a graduate student in the manual group, and I'm doing my equilibrium time setting for realism systems. Sergey, I work with Solano, with social dynamic methods. All right, over there.
So for everybody, especially those who are new, if you have problems with Pauli, go ask Sergey. And Sergey will yell at you and tell you not to do it.
Send you back.
No, but exactly. Sergey will be Sergey is your point of contact if something doesn't work the way that you want it to.
I'm working on like superco or something.
My office, for those who don't know, is right over there.
I'm also a graduate student in the macrosy and electricity solvers. Hi, my name is Pavel. I am a postdoc in Communication Group. I am working on some of the different types of self-consistency that are possible in GW.
My name is Yang. I'm a second participant.
Yeah, hey everyone, I'm Andre. I'm the host of the manual and overall interested in molecular physics, emerging models, and the second solutions for them. Currently, I'm working on completion of version of this inchworm method so that we use it to FT and other things.
Hi, I'm Gaurav. I'm a new postdoc with Dominica. New to the word now. I'm working on disordered systems and trying to combine finite temperature and temperature. Okay. Thanks. Tomorrow's talk, 9 a.m. Lay is going to talk about Phys. All right. Thanks.
Power voltage.
Oh yeah, everybody. Power outage in old Randall from Thursday until Monday. In new Randall, intermittent on Friday and on the weekend. At least as far as I know. So part of this is that Slash research will go offline. That's our synology. But also part of it is that if your office is in old Randall, you should work from home on Friday and on Monday. You're one of those. Yeah, read your email regarding this.
Take all Randall, you start working from home from Thursday.
Yeah, they will. I thought it was Thursday was still fine and Friday was not.
Thursday, 6 a.m.
All right.
Yeah.
Yeah, fine, fine.
Pavel, I have a
You made it.
So you just we moved it to
I woke up
and
with a bad
all the
dream.
changes you
Oh,
have,
it's
you
a-
have not committed with the Q solver. Please do that. I will note it, and I think I added you to the new repository as far as I remember, but I'm not sure. You can check whether you got it right. I can present it again, but then you will monitor it. Okay. After you commit everything and everything. Okay. I will be gone like today and tomorrow, but yeah, you can.
I really need to.
Okay. Yes.
Oh dear. I implement Slash for I implement Slash for Pokhilko as well.
So you said, typically you actually like
So I don't know how fun with but if you think just the wave function, after C has also the stability, right? Equal has to be C has to be when you go to state of the double flow, then the cycle.
Yep. So I guess that will happen. We'll have your system.
So basically,